The best way to visualize a heap, in my opinion, is to imagine your teenage son's floor. If this is the floor, then, well, this is the shirt he wore yesterday. These are the pants he wore the day before yesterday. And basically, it's just all over, right? When he comes home from a long day of school and changes clothes, he's going to take it off and basically find a clean spot, because you wouldn't want to stack his stuff up, and he'd toss it into the nearest clean spot, and the heap just kind of gathers stuff. Internally, you can imagine that the computer is aware of where there's open spaces. And these open spaces happen to be linked together with variables that reference the next one. This is called a linked list. And heaps often use linked lists. This is a gee-whiz detail for your amusement. And when you say to the heap, hey heap, I need a new spot because I've got a new object I need to allocate, it's going to run through its linked list and find an open spot somewhere in the heap and say, okay, this spot now belongs to you. So its list will now, if this spot right here happened to be the size it needed, it'll just kind of get rid of that spot, allow you to throw your object into that spot, and now its linked list will be updated to remember that the blank spots are now here.
Is that lazy programming?
Kind of. You're not going to need to write a heap, but be aware that here's what a heap does. It keeps track of a great big vast area. It knows where the used spots and the blank spots are, and when you say to your heap, hey heap, I need some new memory, and it needs to be about this big, the heap is capable of saying, oh, here's some, you can use it, and then you can use that piece of memory.
Will a heap rearrange?
Yes, in Java it can rearrange. In most languages it never moves anything. And your computer has so much memory that as far as you're concerned, you never need to worry about the heap. It's just there, and it's an infinite resource of all the memory you'll ever need. And that's true until you start programming something that requires a lot of memory, and then you'll get more worried about it. But one of the really nice advances of Java, and languages before it didn't do this very much, is it has something called a garbage collector. Imagine the mother who walks into the room and keeps organizing the objects on behalf of the teenage son. Okay, well, I've described two data structures, and I don't think it's important for you to be too particular about the details. So I'm just gonna do it like this. I'm gonna say stack heap, and I'm gonna draw two boxes. Notice the heap one is really big. That's on purpose because that's sort of how it is in memory. Every programming language provides two built-in data structures for you. They're called the stack and the heap. And they're really useful. And they're being, well, let me put it this way, they're being used whether you know it or not. So whenever you say in a programming language, int I, so this is a variable declaration, right? What that does is it pushes a place onto the stack. So you might have all of these variables already, and when you say int I, it pushes one more slot. We'll call this I. And that's how variable declarations work. Your programming language has inside of it a stack. When you say int I, it pushes something onto the stack. And when you say I is equal to 5, well, it already knows that I means this location on the stack, and so it puts a 5 there. Why am I telling you this? Do you need to know how Java works under the hood? Kinda yeah, kinda no. You can use it without knowing this, but if you really know what it does, in my opinion, things make a lot of sense a lot faster. For example, look at this code right here. Wrapper W. What that really says is, hey, declare a variable, but what that means is push a little slot onto the stack, and that slot will be called W, and now I know about it. What new does is this contacts the heap and says, okay, heap, I need some memory because I'm going to allocate a wrapper object. And how big is a wrapper object? Well, not too big because it only has an int in it, but it could be that maybe wrappers were declared to have 50 variables in it, and wrappers are actually great big giant odd classes objects, right? Who knows? Well, when I say here in this code, wrapper W, let me actually follow the code. That would be more helpful. When I say wrapper W, it makes a variable named W. This is a reference type. I was an int type, W is a reference type. When I say new wrapper, that tells the heap I need enough space to hold a wrapper, and it finds a spot, maybe right here, and it sticks your wrapper object in memory. And what is memory? Inside your computer, you have a chip. That chip has a whole bunch of capacitors, and it keeps refreshing the charge in those capacitors. Or it has a bunch of flip-flops, depending on which type of memory you have. I don't even know what we use in modern computer memory because I'm not a computer engineer, I'm a computer programmer. But somehow they use electrons to represent a lot of ones and zeros. There are billions of them in this chip. So your memory is really just a big array of numbers. But I like to think of it as a bedroom floor, and the heap finds a place in that big array of numbers that's not used and returns it to you. And this line right here, that equal sign that says W equals that new wrapper, well, that new wrapper calls the constructor, which allocates this object on the heap, and the equal sign says put the memory location of that object right here in that variable on the stack, which I prefer to draw with an arrow like that. So basically, this W references an object that's on the heap, and as it happens, that object has inside of it an integer value which had the number 5 in it, if I recall correctly. Okay? And what have I shown you? Nothing that I haven't shown you already. I've just used a little bit more terminology. This time I'm telling you the way declarations work is they push something onto the stack, and the way the heap works is it finds some open space, and the garbage collector wanders around and keeps it clean. It's the maid. But I think the concept of scope will make a lot more sense when you understand that it's a stack, right? When we call into a function, every variable that you declare, int I, int j, or hj, int k, whatever, pushes something onto the stack. When you hit this close brace, what actually happens? It goes pop, 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 and it pops all the variables off until it gets to the same spot, till the stack is the same height as it was when you entered the function. And now if we were to ask the question, why can't I use this local variable, this k, inside of some other function? Because when I'm inside of this function, that's not on the stack. Does that make sense? So when you declare a variable, you add more to the stack. When you return, you pop it all off of the stack. And so your variables accumulate on the stack, but they're always cleaned up when you return, and that's why scope is what it is. It's there because k is only on the stack from this moment until that moment, and this moment pops everything back off of the stack. Have you ever wondered, when you call w.inc and it goes in here and it does w.inc, when it's done, how does it know where to go back to? Well, internally, when you call w.inc, it pushes onto the stack a pointer, a reference to where it was, such that when it returns, it can pop that back off of the stack and say, oh, I was right here, and continue on where it was. So these two data structures are actually all you really need to build a full-on computer programming language, and that's really what Java uses, is a heap and a stack. How do you put something on the stack? You say type name followed by variable name. Type followed by variable, semicolon. This is a variable declaration. So declare puts things on the stack. How do you put something on the heap? You say new. New allocates space on the heap, calls the constructor to initialize it. And how do you connect a variable on the stack to a variable on the heap? You use an equal sign. And the equal sign basically says, hey, the thing that new returned, which is the location of that object, gets placed into the variable. And now what's going on in memory and how that connects to code and what you're seeing in the debugger should all start to kind of come together, and you start to say, this is the moment when it all begins to finally make sense, I hope. All right. And now I can tell you a few more things about programming. How are variables passed? Suppose I have a Boolean b and some class sc as parameters to this function. Now I had better pass something. Boolean b some class sc equals new some class. And yes, this is meaningless code. I'm sorry, I'm doing this on the fly. So I'm passing these two values now to this inc function. When they get passed, where do these values come from, or where do these parameters come from? The answer is the stack. So when you call a function, the first thing that happens is it pushes all of your parameters onto the stack. And then when you're in the function, it knows that b refers to a place on the stack and sc refers to a place on the stack, and its local variables do as well. And when you return, it's all popped back off of the stack, and now it no longer exists. That's how it keeps track of everything, and that's how it all works. Okay? A lot of words. Want to see it in action just so that you have something to attach it to? Okay, let me get some code working. And then I think it's time for a break. So let me do a quick demo and then I'll let you go stew on that. I'm also showing you how to fix compile errors. That's all of them. Build successful. Okay, let's run the program. It prints the number 6. But I also added some extra code just so I can show you what happens. I'll put a breakpoint here, hit debug. I'm now on this line, and if I look at my variables list, unfortunately it's tiny. I'm sorry you can't see it. But right now, the only thing on my list is args. Okay, args is that one thing that was passed in by the operating system to my program. As soon as I call this line, I'll step over. Wrapper w equals new wrapper. There's a w on my stack. And if I open that up, what I'm really doing is I'm following that w onto my heap. So this is w's on my stack, and by opening it, I'm saying, hey, look in memory at that location, follow the arrow to see what's over here. And that's where I'm seeing this 5 from. And now I say Boolean b equals false. What did I just do right there? I pushed a new thing onto my stack. It's called b, and it's set to a value of false. Essentially, what I'm showing you is that this variable window in your debugger is a view of your stack. What you're seeing here is a list of everything that's on your stack, except for the internal things that it doesn't want to show you. And if you open them up, you're following it onto your heap, and so you can see what's out there on the heap. So now, if you can, when you use a debugger, always imagine this picture. This is where your variables go, and when you open them up to see what's in them, you're wandering into your heap and following arrows all over in your heap. And if you can keep straight how memory looks in your computer while you're programming, then all of a sudden everything comes together and you can do a great job. And one thing I wanted to show you now was right here. If I step into w.inc, notice I'm passing a b and an sc to it. I'm going to step in. Here I am right here. There's a b and an sc on my stack. These values were passed as the parameters. These are not the same B and SCs as down below, they're copies of it. It turns out that B is a primitive type, so a copy of a primitive type is just the value false itself. If I change it, it won't get passed back. Whereas SC, this is a reference, so it's a memory location. Yes, this is a copy of the other one, but they're both referring to the same location in memory, so if I change what's there, it'll be more permanent in nature. Okay? When I return, it pops all those things off the stack, and now I'm back to just these things that were on the stack before. And finally, I print my number, and we now see the number 6. That was the end of the program. So you know what's going on underneath the hood a little bit better than you did a moment ago. Okay.